So what we want to do here is we want to study the relationship between examples 17 and examples 18 in chapter 10 on group homomorphisms here. Evidently, applications of the first isomorphism theorem, you do see a factor group right there. Example 17 is not labeled as a theorem standing out as a theorem in the book, but you do see it's called the NC theorem here. What is that about? We have a GZ theorem. Now we have an NC theorem. Let H be a subgroup of G. Noting that the normalizer of H and G is this set and the centralizer of H and G is this set, we're going to say some things about those. Now, we haven't talked about normalizers and centralizers of subgroups. We have talked about centralizers of elements, right? If you had an element A in the group, what's the centralizer of A? Let's recall that. That's maybe the first thing I'll write down. Recall. If A is an element of G, the centralizer of A is not the center of G, right? The center of G is the set of everything in G that commutes with everything else in G. The centralizer of an element is the set of everything in G that commutes with that one element. All the little g's and capital G such that GA equals AG. Okay, I have mentioned that before. That's a subgroup of G. Centralizer of A. But now in this example, we also have the concept of a centralizer of a subgroup. H is a subgroup of G. This is a new concept. The centralizer of the subgroup is everything in G that commutes with everything in H. Everything in that subgroup. Okay, the book uses X instead of little g here, so I guess I'll go ahead and do that. All the elements X in the group that commute with everything in H, written in sort of an atypical way here, by having X inverse on the left side of the equation. That equation is equivalent to this equation, right? You could get from this one that I'm pointing at right there on the right to this one that I'm pointing at on the left by multiplying this equation on the right by X inverse. So this is the same as saying X and H commute. This needs to be true for all H in capital H. Centralizer of a subgroup. If you had an element of H, would the centralizer of that element be a subgroup of the centralizer of H? Or would it be the other way around? You might wonder things like that before trying to read further. You could ask that question. If A is in H, is the centralizer of A a subgroup of the centralizer of H? Or maybe it's the other way around. You could try to answer questions like that. If you commute with A, do you commute with everything in H? Is what would be the thing to ask for the first question. Does that make sense? Does that necessarily sound like it's true? If you're an element that commutes with A, does that mean you necessarily commute with everything in H? Doesn't sound true, does it? Probably we should default to that probably being wrong. On the other hand, if you commute with everything in H and A is in H, then you got to commute with A. This sounds like that's true. Yes. So centralizers of subgroups are evidently kind of smaller, maybe in general, than centralizers of individual elements. Center is also smaller. You might recall, we're just doing a little remembering here. You might also recall that the center of G, the set of elements of G that commute with everything in G, is the intersection of all the centralizers of the elements. So the center is kind of small, relatively speaking, compared to centralizers of elements. And centralizers of subgroups are small compared to centralizers of elements. Just trying to get a little intuition, just trying to remind ourselves of things. This is how you study group theory. You think about these concepts related to what we thought about before and ask these kinds of questions and maybe see if you can give quick mental answers to them. N of H, what is that? That's something new. Normalizer of H and G. Everything in G, what is this saying? This is the condition for normality, isn't it? H is going to be normal in G if this, I call that a conjugate of H, X inverse. Well, the normal subgroup test said if that's just a subset of H, it's good enough for H to be a normal subgroup. Actually, if it's a subset, they actually will be equal. But this is not necessarily saying H is normal in G. It's the set of everything in G where that's true. But that might not be everything in G. H might not be normal in G. So this may not be true for every X in G. But it's true for some subset of X's. In particular, think about it. If X is in H to begin with, then this is going to be true. If X is an element of H, right? Because take an element of H times an element of H times X inverse, where X is an element of H, it's still going to be an element of H. H is a subgroup, it's closed. Is it worthwhile to draw like a Venn diagram here? Maybe. Maybe this is your group G. Maybe this is your subgroup that you're thinking about, H. It does have the identity element. There's E sitting there all by itself. Okay, no, it's not by itself. There's other elements, you imagine, in H. The centralizer of H is everything in G that commutes with everything in H. Guess what? That doesn't have to include everything in H itself, right? H itself might not be abelian as a subgroup. G may not be abelian and H may not be an abelian subgroup. The centralizer of H, well, it's good. Well, okay, I got to make sure I include E. It is going to include E. It may not be a subset of H, though it will include E for sure. What about the normalizer, though? The normalizer, I just said a minute ago, would include H. Would it include everything in the centralizer? You might wonder, is C of H a subgroup of N of H? Centralizer, okay. If you commute with everything in H, will this equation be true? Yeah. The centralizer of H is going to be a subgroup of the normalizer of H. And H itself is going to be a subgroup of the normalizer of H. So the normalizer of H is bigger and includes H and includes C of H. So this green thing might be the normalizer. Once again, this is not giving you a perfect understanding of these concepts by any means, but it's part way toward trying to understand what's going on. If I was going to continue working at understanding these concepts without continuing to read further, I would think about examples. You know, what if G is abelian? Well, maybe these are trivial when G is abelian. Yeah, these things are trivial when G is abelian. They C of H and N of H would be the entire group. So it's only interesting when G is non-abelian. So then maybe you think about non-abelian examples. Maybe you think about S3 or S4, D3, D4, D5, D6 dihedral groups. Think about examples, compute these things, and just try to get a feel for what's going on. We don't have time for that, so we need to continue with the abstract stuff of this example. Turns out these are subgroups of G. H is a subgroup. These are both going to be subgroups. They're going to be closed under multiplication and taking inverses. All right, consider the mapping from the normalizer of H to the group of automorphisms of H given by sending an arbitrary element, evidently, of the normalizer to its inner automorphism, right? That's the notation for an inner automorphism. That equation there. Inner automorphisms are automorphisms, right? We have in G and ought G, in this case, in H and ought H. Every inner automorphism is an actual automorphism, meaning it's a one-to-one and onto mapping from the group to itself. Inner automorphisms are the ones that have the special formulas. Inner automorphisms and automorphisms in general are different. Some automorphisms don't have these formulas. In particular, if your group is abelian, the only inner automorphism is trivial because everything commutes. But there are automorphisms that are not inner automorphisms. So it says this mapping is a homomorphism with kernel C of H. That's probably, the author's claiming this. That's probably something you want to verify. The mapping has not been given a name. Let's go ahead and give it a name. Let's call it our second favorite Greek letter, psi. Psi goes from N of H to aught of H. The formula for psi is psi of G equals phi sub G. The claim is this is a homomorphism with kernel C of H, the centralizer of H. Okay, why is it a homomorphism? We'd have to show it's operation preserving. Is it well defined? Well, that's not really an issue here. We only think about well-defined when you've got mappings from collections of cosets, like factor groups, to some set, or where else did we use well-defined? That was the main place we used well-defined. When you got two cosets that are the same, that have two different representatives, and you're mapping from a collection of cosets like a factor group to something else. So there's no issue with it being well-defined. The only issue is it operation preserving? Oops, sorry. This equals phi G1, G2, whereas this equals phi G1 compose phi G2. Question is, are these things equal? Question mark. This is something the book discussed back in chapter 6 or 7. I think these are equal. You can verify the formulas work. For example, phi G1 compose phi G2 of an element X. I'm talking about inner automorphisms here, so I have to use the formula. Phi G2 of X is G2 times X times G2 inverse. And then if you plug that thing into phi sub G1, you get G1 times this thing times G1 inverse. And the trick here is to use the associative property and the sock shoes property to rewrite that like this. And that's the same as the inner automorphism phi sub G1 times G2 of X. So yes, these are equal. Yes, to this question. We verified that. And that verifies then that these are equal. Yes, like I just said. So it is operation preserving. Psi is operation preserving. It is a homomorphism. Is it onto? Not necessarily. There could be automorphisms in H of H that are not inner automorphisms. Is it one-to-one? Not necessarily. And in fact, it's got a possibly non-trivial kernel. The second thing to verify here is the kernel is C of H. And we verify that here. What does it mean to be in the kernel? What is the kernel of psi? an element G is in the kernel of psi if and only if what? There's the formula for psi. If and only if the element it gets mapped to under psi, phi sub G, is the identity element of the group of automorphisms, which would be the inner automorphism phi sub E. Phi sub E is certainly the identity element of the group of inner automorphisms, in of H, I should say. It's also the identity element of the group of automorphisms, out of H, because, again, inner automorphisms are automorphisms. And this certainly is the identity map. It certainly maps everything to itself. So the question is, when does that happen? Well, that's going to happen if and only if phi sub G of X equals X for all X in what? In H, because we're talking about H here. But by the formula for phi sub G, that's the same as saying Gx G inverse equals X for all X in H, which is the same as saying G commutes with everything in H. Same as saying G is in the centralizer of H. So let me cross off the question mark. The kernel equals the centralizer, just like the author claims. This feels like it's not that, it's like, oh, this is so abstract. Where in the world are we going with this? Hang on, we're getting halfway to the punchline. Punchline is a classification fact. Kind of an interesting, maybe an unexpected classification fact. What do we do with this? Well, we're talking about homomorphisms in kernels. The first isomorphism theorem should be relevant, right? That's when you're talking about groups and homomorphisms in kernels, the main thing you should think of is the first isomorphism theorem. That's how to become more of a group theorist, is to think that way. Oh, the first isomorphism theorem must be relevant. The first iso theorem would then imply what? We're talking about a homomorphism with a certain kernel. The first isomorphism theorem says, take that group, N of H in this case, and mod it by its kernel, form the factor group. And since the kernel is the centralizer, we can also write that like this. That's got to be isomorphic to what? The first isomorphism theorem says it's isomorphic to the image of the homomorphism, which is a subgroup of odd of H in this case. Psi is not necessarily onto, so we're not saying that this is isomorphic to all of odd of H, but it's isomorphic to a subgroup of odd of H. Now, it could be the trivial subgroup for all you know, and so that's not so interesting, but maybe it's a non-trivial subgroup, and maybe that's more interesting. Maybe we can conclude something from that. And that's what the next example does, and that's going to be our punchline, is the next example. All this abstract stuff will lead to an interesting conclusion. What is the conclusion? As an application of this thing we've just proved, essentially, is called the NC theorem. That the factor group of N of H by C of H is isomorphic to a subgroup of odd of H. That's called the NC theorem. As an application of that, we will show that every group of order 35 is cyclic. That's pretty profound. That's a classification. That's a new classification fact, right? What are our classification facts so far? Groups of order P are cyclic, where P is prime. If P is prime groups of order P squared, well, there's only two possibilities. They are abelian, either cyclic or the external direct product of ZP with ZP. We also talked about groups of order 2P where P was prime. Two possibilities there as well. 35 is 5 times 7, not 2 times some prime, not a prime squared. The product of two distinct primes, 5 and 7. This is a new classification fact, and the author is claiming any such group must be cyclic. Surprising. And in fact, the author says it generalizes to the product of any group of order P times Q, where P and Q are primes, P is less than Q, and P does not divide Q minus 1. So, for example, if P was 5 and Q is 13, as another example, groups of order, what would that be? 13 times 5, 65, right? Groups of order 65 are cyclic. Doesn't apply to P is 5 and Q is 11, though, right? Because 11 minus 1 is 10, and 5 divides 10. Groups of order 55 are not necessarily cyclic, but maybe they are. Maybe there's some other fact you can use to prove it. I don't know. Let's look at this example now. For sake of time, we'll try to go through this one quicker. But it probably deserves just as much thinking time if you really want to understand it. All right, so let G be a group of order 35. Trying to prove it must be cyclic. Probably an argument by contradiction is the big idea here. Assume to the contrary it's not cyclic and get some sort of contradiction. By Lagrange's theorem, we do know every non-identity element has order 5, 7, and 35. Lagrange's theorem, fundamental thing to use here. If it's got some element of order 35, it's got to be cyclic. So for the purpose of getting a contradiction, evidently, we may assume that all non-identity elements have order 5 or 7. The next sentence, couple sentences, are pretty important to have some intuition about, and we have talked about this a little bit. However, not all such elements can have order 5, since elements of order 5 come 4 at a time. Does that make sense? We have seen this before. If an element has order 5, if it's a generator of its, well, by definition, it's going to be a generator of a cyclic subgroup it generates. X has order 5, then the cyclic subgroup generated by X is going to have 5 elements. These 5 elements, E is X to the 5th. Five is prime. All the non-identity elements are going to be generators because 5 is prime. This is also generated by X squared. It's also generated by X cubed. It's also generated by X to the 4th. If you're feeling unsure about that, double check it. For example, consider powers of X squared. X squared to the first power is itself. X squared squared is X to the 4th. X squared cubed is X to the 6th, but then I know that X to the 5th is E, so this is the same as X. X squared to the 4th is X to the 8th, mod the exponent by 5, that's the same as X cubed. And X squared to the 5th is X to the 10th, but that is the same as E. Yeah, so elements of order 5 generate cyclic subgroups of order 5, and all the non-identity elements of such a cyclic subgroup are generators of the same cyclic subgroup. So they got to come in groups of 4, so to speak. So what the author is saying is all these other 34 non-identity elements can't all have order 5 because they come in groups of 4 that are all connected to each other. And 4 does not divide 34. So they got to be a mixture of elements of order 5 and 7. Yeah, you need the next sentence. for that as well. Similarly, since 7 is prime, elements of order 7 come in groups of 6 at a time, but 6 also does not divide 34. So yes, G must then have elements of order 7 and elements of order 5. Since G has an element of order 7, it's got a subgroup of order 7. Yep. Take a cyclic subgroup generated by such an element, call it H. Okay, here looks like a key sentence. In fact, H is the only subgroup of G of order 7. Why? Because if K was another subgroup of order 7, back in chapter 7, we had this fact, which I did briefly talk about, and it was in the lectures. It's not a real big emphasis for us, but HK is the set of all products of elements of H with elements of K. It's not necessarily a subgroup of G, actually, unless one of these subgroups is normal, turns out. But you can still talk about how many elements it has, and it was this. And if H and K are distinct subgroups of order 7, this would then have 7 times 7 divided by 1, or 49 elements. Why divide by 1? Because if H and K are distinct subgroups of order 7, the only overlap they have is E. Right? Because the individual elements of order 7 generate cyclic subgroups of order 7 that all generate each other, so to speak, those 6 generators. If you had another subgroup of order 7, the 6 generators would have to be distinct from the original one. So their only intersection is the identity. That's why that's a 1 there. 49 elements, but that's impossible because G has order 35. 49 is bigger than 35. So what did we prove? We proved H is the only subgroup of G of order 7. Since for every A and G, the conjugate of H is also a subgroup of the same order. AH, A inverse. I have mentioned that's a subgroup of G, no matter what H is, as long as H is a subgroup. If H is normal, it equals H. But in general, it's a subgroup. It's got to be another one of order 7. But since there's a unique subgroup of order 7, it's actually got to equal H. So H must be normal in G. And in fact, the normalizer must be all of G, because H is normal in G. We're getting close. Hang on here. It's like, where are we going with all this, right? When I'm reading this for the first time, I don't really know either. It feels like you're just following a rabbit trail, not knowing where it's leading. But we're going to get to the contradiction somehow, evidently. Somebody had to explore this for the first time. Must have been a shocking discovery or at the end, you know. Since H has prime order, it's cyclic and therefore abelian. And so its centralizer contains an H. Hey, remember I mentioned in general the centralizer of H doesn't have to contain H. There could be elements of H over here that are not in the centralizer. But if H is abelian, it would. C of H contains H. H is a subgroup of C of H. H is a subgroup of C of H. So what are we saying? H is a subgroup of C of H. So 7's got to divide the order of C of H. Right? Because H is a subgroup of order 7. Lagrange's theorem. And also by Lagrange's theorem, this divides 35. It's a subgroup of G. Order of C of H is divisible by 7 and divides into 35. I guess it's either got to be 7 or 35, doesn't it? It follows then that, yeah, C of H equals either G, it has order 35, or it equals H, it has order 7. If the centralizer is all of G, we may obtain an element of order 35 by letting H equal H, X equal HK, where H, that sounds like it needs verification. Centralizer of H is all of G. Evidently, this element has order 35 and would be a generator G, making G cyclic contradiction. How does we know that would have element order 35? So H would have order 7 and K would have order 5. in general, you can't multiply the orders of elements to get the order of their product, but when they commute, I believe you can. And by saying the centralizer of H is all of G, you're saying everything in G commutes with everything in H. Not going to take the time to verify that, but I'm pretty sure it's right. On the other hand, if C of H equals H, it's got order 7. Oh, here is where we apply the NC theorem, finally. Lagrange's theorem as well. This factor group is going to have order 35 divided by 7. That's Lagrange's theorem, which is 5. But the contradiction is, by the NC theorem, this has got to be a subgroup out of H, but out of H has order 6. 5 does not divide 6. H has 7 elements. It's isomorphic to Z7. And back in chapter 6, it was said that out of Z, oh, that we should look that up here. Back in chapter 6. Odd of Zn is isomorphic to Un. So odd of Z7 is isomorphic to U7, and U7 has 6 elements. 1, 2, 3, 4, 5, 6. Under multiplication mod 7. Wow. Contradiction. G must be cyclic. Wow. Somebody had to discover this for the first time. But we can enjoy what they did. Such a rabbit trail, so convoluted, but it gets you to a significant conclusion in classification fact and group theory. Groups of order 35 are cyclic, and groups of order P times Q, where P does not divide Q minus 1, are also cyclic. The argument is supposed to generalize. Now, most math people do not like group theory that much, including most math majors, perhaps. Are you somebody like that or not? I don't know. I've really talked to you about it. Maybe a few of you like group theory. If you really like group theory a lot, consider writing it as your senior seminar paper on group theory. And if you're going to pick a topic, what I would suggest picking is something where you do this kind of stuff a lot. That I do talk about a bit in the next lecture, lecture 22, I think it is. Though I don't assign any homework problems about it, and it's not in the exam. It's chapter 23. It's called the silo, don't say silo, silo theorems. It's one of the pinnacles of group theory. It's in the book. I really struggled with it when I first learned the silo theorems. It's not easy. But once you study it enough, you can understand it, then it becomes amazing. It's an amazing subject, really helping you classify groups, really helping you just do unexpected things. Like the punchline of chapter 23. Well, okay, there the author generalizes the example from we just looked at. G is a group of order PQ, or P and Q are primes. P is less than Q, and P does not divide Q minus 1. G is cyclic. And it looks like they were actually using a different argument here. It's actually a shorter argument based on Silo's third theorem, I guess. But another punchline in here is that every group of order 255 is cyclic. Whoa. 255 being the product of 3 distinct primes, 3, 5, and 17. And look, NC theorem must be relevant, it looks like. So if you've enjoyed today's class, and you do like group theory in general, you're the first isomorphism theorem just makes sense to you. You could consider doing Silo theorems for your senior seminar paper next January. Okay, I would encourage you to even. I would encourage you, even if you don't like group theory, to continue studying chapter 10 a little bit. And really do try to develop some intuition about the first isomorphism theorem. This diagram can be helpful. Homomorphism from S3 to Z2. Another example of something that's helpful is actually back in chapter 9, I believe. Yeah, talking about factor groups and thinking about D4 and a normal subgroup of D4, which is R0 and R180. And this Cayley table and how it's structured. I'm not going to go into details, but those are parts of the keys of getting some intuition about why the first isomorphism theorem is true. Not just a proof of it, but just some intuition. It makes intuitive sense to you. Okay, and I would encourage you to work on that.